You know that feeling when you open up YouTube and the recommendation is just perfect? It's exactly what you wanted to see, but you didn't even know you wanted to see it.
Yeah, it can be a little unsettling, can it?
It really can. And, we call it magic or we say the algorithm is reading our minds, but it's really just we're swimming in this invisible ocean of math.
It's the invisible infrastructure of our entire modern life. It's not just YouTube. It's what you buy, how you get a ride, and increasingly how you even think.
Exactly. And so the whole mission for this deep dive is to stop calling it magic and start to actually see the gears turning behind the curtain. We're going to unpack machine learning, the history, the business side of it, and yeah, even the math that seems so scary.
Well, before we even touch the math, we have to clear up the vocabulary. I mean, I hear people use AI, machine learning, and deep learning as if they're all the same thing,
Hmm.
and they're just not.
Oh, it's the classic buzzword salad. You see it in headlines all the time. They just use it interchangeably.
They do. The easiest way to think about it is like Russian nesting dolls. The biggest doll, the one on the outside, that's artificial intelligence, AI. It's the big, broad dream of making machines act smart. That idea has been around since, the 50s.
So AI is the umbrella term, the big idea.
Right. Then you open that doll up, and inside you find the next one, machine learning. And this is where things get practical. It's a subset of AI where we stop explicitly writing rules like, if this, then do that.
Uh-huh.
Instead, we feed the machine a ton of data, and we let it figure out the rules for itself.
So, okay, traditional programming is me telling the computer if it has whiskers and pointy ears, it's a cat.
Precisely. That's rule-based. Machine learning is giving the computer a million pictures of cats and just saying, these are the answers. Now you figure out what makes them all cats.
And what's in the very middle, the smallest doll.
That's the tiny, super intricate doll in the center, deep learning. That's the real heavy hitter today. It's inspired by the biology of our own brains with these things called neural networks. It's what's driving this whole generative AI boom we're seeing right now.
Okay, so AI is the dream, ML is the method, and deep learning is the high-powered engine.
That's a great way to put it. And the relief here for most people is that ML isn't magic. At the end of the day, it's just math finding patterns in all the noise.
It's funny you mentioned the brain because I was actually surprised to see the roots of this go all the way back to the 1940s. We're trying to copy biology before we even had the chips to run any of this on.
We were. There was a guy, Donald Hebb, back in 1949, who proposed this idea. Cells that fire together, wire together.
Right.
It's the biological basis for how we learn.
Right.
And that concept, strengthening connections based on activity, is literally how we design weights in digital models today.
So we basically stole the blueprint from our own heads. If two brain cells are active at the same time, their bond just gets stronger.
Exactly. And if a connection isn't useful, it gets weaker over time. It's like evolution, but on a microscale. Then, in the 50s, Arthur Samuel took it a step further. He actually taught a computer how to play checkers.
This was the guy who coined the term machine learning, wasn't it?
He was, yeah, back in 1952. His program was revolutionary because it used what he called rote learning. It remembered every board position it had ever seen. It didn't just play the game, it studied it.
And then came the perceptron, which I have to say sounds like a villain from Transformers.
It does sound pretty ominous. But yeah, in 1957, Frank Rosenblatt created the Mark I perceptron. And here's the wild part. It wasn't software. It was a physical, hulking beast of a machine built for image recognition.
That didn't quite work out, did it? We kind of hit a wall.
A massive wall. The perceptron it couldn't recognize complex patterns like faces. It couldn't handle the nuance. And that failure made investors get really cold feet, which led to the first AI winter.
Yeah.
All the funding just dried up.
Which leads to what our sources call the Great Schism in the late 70s. It sounds like a messy divorce in the computer science world.
It really was. You had the AI camp on one side and the ML camp on the other.
So what were they even fighting about?
Well, the AI camp was obsessed with pure logic and reasoning. They were trying to perfectly simulate a human mind, symbol by symbol. But the ML camp basically said, look, forget the philosophy, forget building a fake brain. Let's just use probability and statistics to solve real, specific problems.
So they stopped trying to build a conscious robot and started building, really, really good calculators.
And that pragmatism is what saved the entire field. By focusing on boring, service-oriented problems like filtering spam or routing trucks more efficiently, ML started to flourish in the 90s. While the AI dreamers were stuck, the ML statisticians were actually delivering real value.
And that's what's brought us here. So let's talk about how these machines actually learn today. Because they're not sitting in a classroom with a textbook.
Far from it. We usually break it down into 4 main flavors. The first, and by far the most common, is supervised learning.
This is the teacher analogy, right?
Yeah, exactly. You have a teacher who has the answer key. You show the model a picture and say, this is a cat. You show it another and say, this is a dog. You do that, a million times until it can do it by itself.
And within that, you have regression and classification. Classification, I get. Is it a cat or a dog? Is this email spam or not spam? But what's regression?
Regression is just predicting a number. So based on its size and location, what will the price of this house be? Or predicting tomorrow's temperature down to the decimal. It's all about continuous values, not categories.
That seems pretty straightforward. But what happens when you don't have an answer key? When you just have a giant, messy pile of data?
Well, that's unsupervised learning. You basically just dump a massive pile of data on the machine and say, go find the patterns. You don't tell it what it's looking for.
And this is where we get the famous beer and diapers story.
It is. And like whether the story is 100% historically true is, debatable, but the principle behind it is what matters. The legend comes from Walmart. They analyzed their sales data using unsupervised learning, specifically something called association rules, and found a really strong correlation.
Okay.
Men who were buying diapers on Friday evenings were also very often buying beer.
Which, it makes sense when you think about it. New baby at home. You're not going out to the pub. You're having a beer at home. But a human manager might never think to look for that.
Exactly. A human looks for logical links, like putting the chips next to the salsa. The machine just looks for statistical links, no matter how weird they seem. So Walmart apparently put the beer next to the diapers, and sales for both went up. That's the power of it. It finds invisible connections.
Then there's reinforcement learning. You called this the gamer one.
Yeah, this is all about rewards and punishments. Think of an agent in a video game. If it walks into a wall, it loses a point. If it finds a coin, it gets a point.
Like AlphaGo, the program that beat the world's best Go players.
Exactly like AlphaGo. It played millions of games against itself. It didn't have a teacher showing it the best moves. It just learned through trial and error that certain actions led to winning and others led to losing. It brute forced its way to genius.
And the last one, semi-supervised learning. This feels like the practical, budget-friendly option.
It totally is, because labeling data, having a human sit there and manually tag cat, dog, cat, that's incredibly expensive and time-consuming.
Right.
With semi-supervised, you just label a tiny amount. Say you label one photo of your mom in Google Photos. The system uses that one little clue to figure out the rest of the thousands of unlabeled photos.
So it uses the small labeled set to make sense of the giant unlabeled one. It's how Google Photos works.
Exactly. It's all about efficiency.
It's just wild how these different approaches power things we use every single day.
Yeah.
I want to pivot a bit to the real world, but specifically the B2B, the business-to-business side. Because we all see the consumer stuff, but the business applications are where it gets crazy.
They really are. Let's take retail and inventory. You mentioned Amazon before. They don't just, stock every item in every warehouse.
Right, the Source had that great Indian festival example.
Exactly. Before a huge sale like that, they use ML to predict demand region by region. They literally move stock to warehouses closer to where they predict the buyers are going to be before the sale even starts.
So they're shipping the product closer to me before I've even decided to click buy. That's intense.
It's predictive logistics. Then you have the supermarket profiling example, this one. This one makes people a little uneasy.
This is the big bizarre example.
Right. They use your phone number to track everything you buy. If you're buying kale and protein powder, you get tagged as health conscious. If you buy chips and soda, you get tagged as, well, something else.
And they don't just keep that information for their own flyers.
Oh, no. They can sell that profile to other businesses. So a local gym might buy the list of phone numbers for all the health-conscious shoppers to target with their ads.
Wow. Okay, that explains a lot of random texts I get. What about transportation? Surge pricing. Everyone hates it. Everyone thinks it's just pure corporate greed. But there's a logic there.
There is a logic beyond just making more money. It's a supply and demand balancing act. If you're Uber or Ola and suddenly demand skyrockets in one neighborhood after a concert, you have a problem. Too many riders, not enough drivers.
So the higher price isn't just to gouge the person who needs a ride. It's a signal to the drivers.
It's a direct incentive. A driver in a quiet part of town sees the surge price and is motivated to drive over to the busy area. It's an automated market correction. Without ML predicting that surge and adjusting the price, you probably wouldn't get a ride at all.
And then there's manufacturing. Tesla is a huge example here.
Tesla is a great case for what we call predictive maintenance. Their factories are full of robotic arms, and those arms are covered in sensors monitoring heat, RPM, vibration, everything.
So instead of waiting for an arm to break down and shut down the whole production line,
The ML model notices, hey, the temperature on arm number 7 has drifted 2 degrees higher than normal for the last hour. It predicts a failure before it happens. They can schedule a repair during a normal break, which saves them literally millions in downtime.
that's just smart. Okay, last one. Sentiment analysis. The source mentioned this was used a lot in the 2014 India elections.
Right. Instead of slow, expensive polling, analysts just scraped millions of tweets. They trained models to look for positive or negative sentiment about the candidates.
And stock traders were using this.
They were. If the sentiment analysis predicted a win for a candidate who was seen as business-friendly, traders would start buying up stocks of companies they thought would benefit. They were basically making financial bets based on the mood of Twitter.
Incredible. Okay, I have to pause this here and look under the hood. Because when you read about this stuff, you hit this wall of, like, terrifying math terms. And the big one is tensors.
It really sounds like something from a Marvel movie, doesn't it? We have to secure the Tesseract.
It really does. But you're telling me it's just a bucket for numbers.
That's all it is. A tensor is just a container for data. To make sense of it, just picture a basic spreadsheet.
Okay, I've got Excel open in my head.
Great. One single cell with one number in it. That's a 0D tensor, also called a scalar.
Okay, simple enough.
An entire row of numbers in that spreadsheet. That's a 1D tensor, or what we usually call a vector.
And the whole grid, the whole sheet.
That's your 2D tensor, a matrix. It has rows and it has columns.
Okay, I'm with you so far. But then the sources start talking about 3D, 4D, even 5D tensors. I mean, how do you even visualize 5 dimensions?
You don't, really. You just build it up. So imagine stacking a bunch of those 2D spreadsheets on top of each other like a deck of cards. That's a 3D tensor. We use that for things like time series data like stock prices over many days.
Okay. What about 4D?
Images.
Wait, how is a single picture 4-dimensional? It looks pretty 2D to me.
Well, an image has a height and a width, right? That's 2 dimensions.
Yeah.
But it also has color channels, usually red, green, and blue. That's your 3rd dimension. And when we're training these models, we don't feed them one image at a time. We feed them a batch, like 100 images at once. That batch number is the 4th dimension.
So, height, width, color, and which number image it is in the stack.
Exactly. Now, to get to 5D, just think about a video.
A video is just a bunch of images in a row.
Right. So you take that 4D tensor for a batch of images, and you add the dimension of time, the sequence of frames. Now you have a 5D tensor.
That feels like a staggering amount of data.
It is a 1-minute video at 30 frames per second. It's a massive, massive brick of numbers. And that's exactly why we need specialized tools like TensorFlow. They're built to speak the language of these multi-dimensional buckets of numbers.
So we have the math, we have the flavors of learning, but how does a model actually live in the wild? They can't just be train it and you're done, right?
No, absolutely not. That's a huge rookie mistake. There's a whole process we call the MLDLC, the Machine Learning Development Lifecycle, and it starts with a lot of grunt work.
Cleaning the data.
We call it pre-processing, yeah. Removing duplicates, fixing errors, handling missing values. You know, you can't cook a gourmet meal with rotten ingredients. And then you do ED exploratory data analysis, which is just looking at your data to even understand what you're working with.
And once it's finally deployed, you have a choice to make. This is the difference between batch learning and online learning.
Right. So think of batch learning or offline learning, like studying for a final exam. You cram all the information, the training data at once. You build the model, deploy it, and that's it. It doesn't learn anything new until you decide to retrain it next semester.
So if I'm Netflix and I train my recommendation model on a Sunday,
It won't know what you watched on Monday until they retrain the whole system, maybe next Sunday. It's good for stable things, where the patterns don't change much.
but the hardware we have now lets us do this in real time,
Yeah.
which brings us to online learning.
Exactly. Online or incremental learning is like learning on the job. The model updates instantly with every new piece of data. YouTube is the perfect example. You click on a video, the model learns. You skip a video, the model learns, okay, they don't like that. It's constantly changing while you use it
That sounds way better. I mean, why doesn't everyone just use online learning?
because it introduces a massive risk. We call it model poisoning.
Poisoning.
Yeah. If you feed bad data into an online model, think about internet trolls teaching a chatbot to say horrible things, or spam bots clicking on random ads to confuse the system, the model learns that bad behavior instantly.
It adapts to the garbage immediately.
Immediately. With batch learning, you at least have a chance to inspect the new data before you retrain. With online learning, the data is flowing straight in. It requires constant, heavy monitoring, or your model can go completely off the rails in a matter of minutes.
It's a real high-wire act. And that actually leads me to one last kind of slightly terrifying thought from all this. So we've been talking about how these models learn from our behavior. I click a link, it learns. I skip a song, it learns. But if the algorithm is curating my entire reality, showing me only what it predicts I'll like.
You get stuck in a feedback loop.
Exactly. Are we really training the machine? Or is the machine, by narrowing our world and our choices, actually training us to be more predictable? Because, I mean, a predictable human is a lot easier for a tensor to model than a chaotic one.
That is a sobering thought, that we might be subconsciously making ourselves less random just to make the math easier for the machines that watch us.
Something to chew on the next time you're scrolling. Next time you open an app, don't just see the content. See the tensors. See the probability machine at work.
See the math.
Thanks for diving deep with us. We'll catch you on the next one.